Visbreaking or viscosity breaking is a mild form of thermal cracking. This process was developed in the 1930s. My talk today is on a variant of the visbreaking process called Soaker Visbreaking, in which the majority of conversion occurs in a reaction vessel called the soaker that holds the two-phase effluent coming out of the furnace to allow cracking to occur for a predetermined length of time before being quenched. And the oil is then passed to a fractionator to produce fuel oil of the desired specifications. A Soaker Visbreaker uses lower temperatures than in coil visbreaking. The comparatively long duration of the cracking reaction in the soaker is used instead to achieve the desired results. My focus today is on the design of the soaker drum. And specifically, I want to talk about the use of internals within the soaker drum to prevent the degree of back mixing that is undesirable. For further background, I refer you to the papers of Spate, Joshi, published in 2008, Industrial and Engineering Chemistry. My presentation today is a follow-up of a previous presentation on my YouTube channel titled Soaker Configuration and Visbreaking. The early designs of the soaker vessel consisted of an empty drum, as shown here. The two-phase mixture emerging from the furnace enters the drum and flows through the soaker vessel. The gas liquid hydrodynamics in this column corresponds to that encountered in a bubble column operating in the turbulent regime. And given that the soaker vessels are significantly large in diameter, there is a high degree of back mixing in the vessel. This high degree of back mixing leads to a wide residence time distribution, and consequently there is overcracking of the hydrocarbons within the vessel. Furthermore, there is a downflow of liquid along the walls of the column, leading to coke deposition and perhaps coke buildup. In more recent times, the desire to reduce the amount of thermal liquid phase back mixing in the soaker vessel has led to the introduction of internals in the column to prevent the high degree of back mixing. I just show here two configurations: a sieve plate with downcomers and a sieve plate without downcomers. The several configurations used for the soaker internals are described by Joshi and co-workers in this paper published in Industrial Engineering Chemistry in 2008. Let's have a quick look at the hydrodynamics of a vessel consisting of a sieve plate without downcomers. In particular, let's focus on gas liquid flow around the sieve plates. In my laboratories in Amsterdam, we investigated the hydrodynamics of sieve plate columns without downcomers. This is the photograph of an experimental unit, and I show here some sketches to show gas liquid flows up a bubble column with sieve plate internals. What is important to note is that for gas liquid up through the column, we need to have sufficient momentum to drive the gas liquid mixture up the column, and we have the development of a gas cap below the sieve plate that builds up, and the height of the gas cap is dependent on the column diameter and the gas velocity. There is also some degree of liquid exchange between the two compartments, and within a single compartment you may assume that the gas liquid flow is well mixed. And by introducing several plates, say we compartmentalize the column to achieve, say in this case, 4 well mixed stages. Let's look at the development of the gas cap. Experimentally, we determine the height of the gas cap as a function of the superficial gas velocity in the partitioned bubble columns. And I show here experimental data obtained in my laboratory for 3 column diameters. The triangles are for a column diameter 10 centimeters. The squares are for a column diameter of 15 centimeters. And the circles are for a column diameter of 38 centimeters. We note that the gas cap is significantly lower for the larger diameter column. Let's try and understand this variation by carrying out CFD simulations for a partitioned bubble column. The background information is available in the papers listed here. Catalysis Today, published 2001, and Catalysis Today, published in 2003. We carried out CFD simulations in the Eulerian framework to determine the gas liquid hydrodynamics in partitioned bubble columns. The sieve plate partition plates are located here. Consider 3 different column diameters, 10 centimeters in diameter, 15 centimeters in diameter, 38 centimeters in diameter, corresponding to the experimental setups for which the data was presented in the foregoing slide. Initially, the column is filled with liquid. This is the scale to determine the liquid holdups. Red indicates a liquid holdup of 1. Blue indicates a liquid holdup of 0. Liquid holdup of 0 means gas. So initially we have a gas at the top, liquid at the bottom. Gas at the top, liquid at the bottom. Gas at the top, liquid at the bottom. This is where the sieve plates are located. Let's have a look at the gas liquid hydrodynamics as determined from CFD simulations. This is the simulations show the development of the gas cap, because the blue regions are rich in gas and the red region is liquid and rich in liquid. So there's liquid downflow here, and a significantly large gas cap builds below the partition plate. This is in agreement with the experimental data I showed in my previous slide. Let's move on to a column of 15 centimeters in diameter and have a look at the animations of the CFD simulations. Again, we see the buildup of gas cap below the partition plate, but in comparison with the gas cap for the 10 centimeter column, the gas cap here is considerably shorter in height. But you will see here again a red region indicating liquid downflow here. Remember, in the context of the soaker vessel, liquid downflow near the walls would lead to coke deposition of the walls, as is observed in industrial practice. So the introduction of sieve plate partition plates would certainly reduce the degree of back mixing, because each compartment corresponds to one well mixed vessel. And if we have several sieve plate partition plates along the height of the soaker vessel, we would have say 4 or 5 well mixed stages. But that does not imply that the wall flow is reduced. Indeed, there are nooks and crannies created due to the introduction of the sieve plates. Indeed, you see here a large region which is red in color, indicating pure liquid, and this would lead to perhaps coking and clogging of the sieve plates. Let's have a look at the animation for the 38 centimeter column shown here. As is obvious from the blue region here, we have a gas cap that is shorter in height than for the 15 centimeter column, and we see there is a considerable degree of sloshing. We again see a liquid rich region that is indicated in red, and we have regions in which there is liquid stagnancy. The message that emerges from these CFD simulations is, indeed, we have reduction in back mixing, but this is concomitant with dead regions in which there is a high residence time of the liquid, and these dead regions would lead to coke deposition in soaker vessels fitted with sieve plate partitions. So reduction of back mixing is just one positive aspect of soaker vessels with internals, but it appears certainly qualitatively based on the CFD simulations that there is a real danger that there will be dead zones and high residence times of liquid in certain portions of the column. So we need to have a rethink of the use of partitioned bubble columns as the soaker configuration to be used in practice. Let's draw up a wish list for the configuration of the soaker vessel. We need to have an adequate amount of the liquid phase residence time, and the degree of back mixing in the liquid phase should be suppressed so that the residence time distribution is narrow, and overcracking is prevented. Concomitantly, I would suggest that the vapor residence time should be short because the vapor already contains the correct products, and we do not wish to overcrack the vapor. So vapor staging is neither required nor is it desirable. Now, in the visbreaking process, there is a tendency for coke to deposit on the walls of the vessel, and the internals, such as perforated plates, are susceptible to clogging. Therefore, for ease of maintenance and cleaning, there should be no nooks and crannies in the soaker. We should avoid baffles and obstructions in order to prevent coke deposits and clogging. I'm setting up this wish list in a manner that has been suggested in the past in the paper by myself with my colleague C. This paper is termed Strategies for Multiphase Reactor Selection. That summarizes how one goes about selecting the right reactor configuration for any process task. The wish list for the soaker vessel that was set up in the previous slide is met completely in the soaker configuration that is shown in the schematic here. The two-phase mixture leaving the furnace enters a long, horizontal, shallow vessel. And this vessel is empty, contains no internals, and no internals are necessary. If we look at the gas liquid flows within the horizontal shallow vessel, there will be vapor being formed as the liquid traverses the horizontal vessel, and the vapor in the form of bubbles will leave the column and can be recovered. The gas liquid contacting pattern is cross current. This cross current contacting is desirable because once the vapor is formed, there is a danger of overcracking if it remains too long within the vessel. So cross current contacting of liquid and vapor ensures short vapor residence time. For the liquid phase, however, we need a long residence time and low degree of back mixing. For a shallow horizontal vessel, we will have a series of well-mixed stages, and each well-mixed stage corresponds to a section of the column in which the height of the dispersion is equal to the length of that stage. So if the H divided by D ratio is 1, we will have approximately one well-mixed stage. So in this drawing here, we would have, say, one well-mixed stage, two well-mixed stage, 3, 4, and 5, and say between 5 to 6 well-mixed stages would correspond to plug flow of the liquid phase. There is absolutely no necessity of introducing baffles within the column. Indeed, introduction of baffles is undesirable because this would lead to stagnant regions. So baffles are neither required nor are they desirable. I'll leave with the thought that current Soaker designs, to my way of thinking, using partition plates are not to be recommended. These do not meet the process requirements for visbreaking even remotely.